I'm going to make a series of videos for developing a comparator circuit, so comparing between two binary numbers. So for the purpose, this video will do the equality test between two binary numbers. So let's say two binary number, one is this one, a3, a2, a1, a0, other one is b, which is b3, so they are 4-bit. So if I want to say that these numbers are equal, that means this will be equal to this one, this will be equal to this one, this will be equal to this one, and this will be equal to this one. Only then we can say A is equal to B. That should be the equality test. So for the equality test, we have to do a bitwise test. So let's call this, first we check whether A0 and B0 are equal. So for that purpose, if they are equal, that means they're either both of them are 1 or both of them are 0. So if we build a circuit or a logic when both of them has to be equal for the output to be 1, that means either both of them ANDing, that means when both are 1 we will get a 1 here, or like that you can do A0 B0. That means when both are 1 we can get a 1 here, or when both are 0 we will get a 1 here because it's inverted like that. If one of them is 1 and the other one is 0, we will get both of them will be 0 because this one will be 0 and this one will be 0. So these are the two conditions, that is, we can call that equal. Now if we look at it, this means this is for the equality of bit 0. So we can say this means that bit 0 is equal to bit A0 is equal to bit B0, so or A0 is equal to B0, so the least significant bits are equal. Now this one is also, if I write the truth table, this is like that. 0 1 is a 0, 1 0 is a 0, 1 1 is again a 1. So this is the thing, and this one is actually, if I look at the truth table of this one, this is actually an XOR gate, which is this one. XNOR gate, sorry, XNOR. XOR is when the invert of that, so this is XNOR and XOR would be like that. So when they are not equal, the output will be 1. That's the XOR gate. This is an XNOR gate. So A0 B0 test E0. So when they are equal we will have a 1 here. If they are not equal we will have a 0 here. So equal gives a 1 and not equal gives a 0 at output E. Similarly, the exact same case for E1. Again bitwise test, so that will be A1 B1 or A1 bar B1 bar. E2 will be just like that, A2 B2 or A2 bar B2 bar, and E3 will be, so it's just the same thing, B3 plus A3 bar B3 bar. So we have to develop draw all these gates for the circuit to be complete. So it will be this, the whole circuitry will be something like this. If I draw, it's just 4 of these XNOR gates. So basically 4 of them. One I will draw here. So all of them are coming here. So this is probably A1 B1, A2 B2, and here I have A3 B3. So for all the numbers to be equal, all of them, each of them has to be 1. So this one will be 1, this one will be 1, this one will be 1. So the final test result can be found by just ANDing the whole thing. So if A is equal to B, we will get a 1 here. If A is not equal to B for any reason, maybe all these 3 are equal, but these are these two are not equal. In that case we will have a 0 here. So we will have a 0 here for this case when these two are not equal. We will have 1 here, but because they are ANDed we will get a 0 here. So the result will be not equal. So this is how we can build a comparator circuit that can test whether two binary numbers are equal or not. So yeah, this is just the equality test. Then I will do the greater than less than test later on. So yeah, this one is E1 here, E2 here, and this is E3 here. So and also in terms of just the expression, Boolean expression, it will be like this. So if A is equal to B, it will have E3 and E2 and E1 and E0, sorry, and E0. Or we can say that X naught. So if I write like that, A0, B0, A, if I don't want to write the E expression, so they're all ANDed, A2, X naught, B2, and then ANDed A3, X naught, B3. So that's how they are all of them ANDed here, and that means if that's the test of equality. So we can say A is equal to B, which is their equal, like that.